Hey everybody! The purpose of this video is to hopefully explain the sample size calc, SSZECALC program I gave to you guys in class. This is the program, you might remember, explains to you, or it gives to you how many elements you should sample from your population randomly to accurately study the population proportion using p-hat with its margin of error. So the formula itself is derived from the margin of error formula that we spoke of in the previous video. So we'll start up here. Your margin of error for a population proportion p-hat is going to be z times radical p-hat q-hat over n. And what's kind of cool about this formula is you can see where we have to be already. That's what we're interested in. We're interested in how many we should sample to get to our set level of confidence. So we're going to do some algebra first. And those of you that don't like algebra can kind of pretend this isn't happening for the next 2 minutes. But I'm going to solve this bad boy. I'm going to change this just to e rather than dealing with all this variables. So we're going to rename this e for margin of error. So it's going to be z radical p-hat q-hat over n. Let's see, what should we do first? I think I'll divide by z first. So we'll get e over z, and that's radical p-hat q-hat over n. Let's square both sides to get rid of that radical. So we're going to get margin of error squared over critical value squared p-hat q-hat over n. Now we're going to use one of those awesome rules from algebra. Since we have a pure proportion here, I'm going to flip both numerators and denominators, which is pretty fun. So we're going to have on this side z squared over e squared equals n over p hat q hat. Just a word of warning, a side warning. You can only do that when you've got a pure fraction equal to a pure fraction. When I say pure fraction, that means there's no 1 plus or minus n or anything like that going on. So as long as it's a fraction equals a fraction, then you're good to go with what I just did. All right? And we're almost done, aren't we? All we got to do now is multiply by these bad boys. And then we're going to have z squared times p hat q hat all over e squared equals n. And that, my friends, is the size of your sample. Go get this many items, whether it's people, whether it's responses, whatever it is. Z squared, p hat, q hat, all over e squared. Of course, it sounds like gibberish. And here's the deal. This is 4 variables. Well, technically 3. Technically it's 3. Z is going to be the critical value that you're using once you've decided on what confidence that you want. We generally use this as 1.96-ish for 95% confidence. E, or your margin of error from before, that's your maximum desired margin of error. So you have to decide in the beginning, okay, how off will I allow myself to be at worst? Is it 3%? Is it 4%? Is it 1%? You have to decide that off the bat, because that's part of the calculation. So these 2 things you can't get around. And if you remember from the program I gave you, the first 2 things it asks you are, what's your confidence and what's your margin of error? Okay, what I don't ask you, I don't have any prompt for p-hat. And you can figure out if you have p-hat, you're automatically going to have q-hat. Now here's why I didn't prompt you for that. I set the program up, as statisticians will do in the real world, to have the sample size by default be as large as possible to minimize potential error. Now the only way to minimize potential error, when I say error, I mean margin of error and being wrong about your estimate, so being outside of that margin of error. So the only way to make sure that we are outside of it as little as possible is basically to sample enough to get a close enough estimate. I can't change my confidence, and I can't change that maximum allowable margin of error that once I've picked it. This is kind of weird though. If we're studying a proportion, it seems kind of strange that we have to use that proportion's value in the formula while we're it's like a chicken-egg thing. I want to study a proportion, but in order to study the proportion, I need to have the value of the proportion to calculate the sample size that I have to do the study. That seems weird, right? And what a lot of folks will do, what a lot of textbooks will say to do is, well, use a pilot study. Whatever your pilot study was in the beginning, use that value of p hat and assume that your next study will be close to that. Okay, that might very well be fair. I'm sure Gallup does that quite a bit. But I have a better solution. I'm going to pick a value of p hat, and therefore by default q hat, that's going to make this sample size as large as possible. More, as long as it's good data, is better than less good data, all things being equal. So the question is, what values of p hat and q hat make this as large as possible, assuming that you've set z and e? The answer, which we'll explain algebraically in the next video, is let p hat and q hat both equal 1/2. Let them both equal 1/2. And if they both equal 1/2, the product of this quantity right here and quotient product, this quantity right here, will be as large as possible. So if you let that happen, their product becomes 0.25. And the formula for sample size becomes 1/4 times your confidence, your critical value squared, all over your maximum margin of error squared. That is what your TI is running in the sample size calc program. What I'll do in the next video is I'll explain to you why p hat and q hat equaling 1/2 generate the largest possible sample size here. Cool, we'll do that next.